your screen, your sharing?
Let me
Recording in progress.
Everything's fine. So I can share the screen.
Okay, perfect. And we can hear you very well. So
okay.
So that's perfect. Okay.
Thank you.
So Katerina, we can go back to your presentation and yeah, so I see the numbers going up and people getting in. So I will start slowly. So welcome everyone to the 4 p.m. UTC session of this Thursday of LPHYS 2023. So we are going to have a very exciting session with several talks. So I'm pretty sure everyone is looking forward to learn about the talks that we are going to listen about in this session. And the first talk is going to be given by Professor Catarina Riconda from Sorbonne University, and she's going to talk about semi-analytical model for pair production via laser and electron photon beam interaction in the shower regime. So please, Catarina. Well, we can't hear you yet, so your microphone is off.
Yeah. Okay.
Yeah,
now
perfect. Okay. Thank you.
So first of all, I wanted to thank you for the introduction and thank the organizer for inviting me. It's really a pleasure. It was very interesting so far. And of course, this work has been done in collaboration with many people. And one of them is Mathis Pouilles, that is our PhD student in the group, and other collaborator from my laboratory, Luli, and also from GOLP in Lisbon. Okay. So, okay. I can see the problem starting. Okay, let's switch. Please. Okay, good. Okay, so as there will be a bunch of talks and after and already before, but we all expect the multi-petawatt laser that are now available worldwide will allow abundant pair production by laser electron beam interaction. And of course, the accent is on abundant. So we're hoping really to have a large number of pairs with typical interaction of, in an all-optical setup, electrons created by one laser interacting with another laser. Or we can also think about another setup where the electrons that are produced, they can be used with a high-Z converter to produce the other particles and hard photons. And the B-field detector will deviate the particles so that we can envisage real light-light interaction with photons and laser. So in these frameworks, what I'm going to talk about is how to model multiple events of hard photon emission and pair creation. So the two main mechanisms were already introduced, but I'm just going to give you some notations and just remind you the basics. So first of all, we can have that electrons interacting with intense laser, they can produce hard photons, and this is the nonlinear Compton scattering phenomena. And these photons, they can introduce at the turn with the laser and produce pairs by the nonlinear Breit-Wheeler. And these two mechanisms, formally, they have rates of production that are very similar. So this is what is shown below here. But there are two important differences. So the first difference is that while the electrons, even at low key, they will continue emitting photons. Instead, for the per production, we have these exponential terms that actually says that low key per production, it will be strongly suppressed. And I'm not introducing the key parameter in this community, but here is a definition. It's basically the quantum parameter that is, for the case of the electron, the field with respect to the Schwinger field, since it's the reference frame of the electron. Other quantities that I'm going to use is the normalized electron or photon energy. And also these are rates, but I'm also going to use differential rates in the following. So I'm defining them here. And so, as I said, there is one important difference between those two phenomena is this exponential term. And the second important difference is that when you consider nonlinear Compton scattering, one same electron can, in further time during its interaction with the laser, produce photons, more than one photon. While instead, in the nonlinear Bright-Wheeler, once the photon has produced pair, it will disappear. So this leads me to the introduction of what we called a generation. So basically, we say that the same electron emitting multiple photons during this interaction with the laser will produce one generation of photons. So one generation of photons can be filled with many photons. And instead, a photon that with disintegrated emission will produce one generation of pairs, but in this generation, you only have one couple of pairs per photon. And this is useful for the following. And also, again, names. I'm going to call 0 the generation of the beam that is interacting with the laser. So the initial beam is my generation 0. And I will consider this either with initial photon beam or electron beam. But here there is this example of an electron. And so this is generation 0. The electron will survive during this interaction with the laser, produce many photons. All the photons produced by this electron are generation 1. Then the pairs produced by this one generation 1 photon are generation 1 electron positron, etc., etc. So this is a concept that I will use after and I need to introduce. Okay. So in general, if, as I said, what is interesting for us is to have multiple events. So we want to consider the governing equation of the full system, that is the system of electrons interacting with the laser and photons interacting with the lasers. And these are the full equations in 1D approximation. And basically, you can see that the evolution of the distribution function of the electrons will have some, it will be replenished by electrons that had higher energy, and they lose some energy because they emit a photon and they get to the gamma E energy that I'm considering. And it will instead have some losses because of the electrons that have initial energy gamma E, and they emit some photons and then they lose energy. So this is why you have a minus sign. And of course, you will have also new electrons that are created by the pair creation process. So this is the evolution of the distribution function of electrons, and same identical things for the positrons. And then you have an equation for the evolution of the photons. And of course, this will be replenished by the photons created by the nonlinear Compton scattering, and instead it will have losses because of the decay. So this is, well, you can solve this problem. This is a set of equations, but it's quite complicated. You cannot do much analytically, so we try to simplify the problem. And to simplify the problem, we introduced this idea of generation that I was telling you about, and we use this to cut our system to a finite number of generations. So I'm going to consider separately the case of an initial electron beam and an initial photon beam. So the first case I'm considering is the collision of an electron beam with the laser. So I start with a monoenergetic electron beam at energy gamma 0. And for the moment, I'm just going to describe you how you can calculate the pairs produced in the first generation. So you can decompose the distribution function and consider only the evolution of the distribution function of the initial beam. And this is what this formula gives. Once you know that, you can calculate the distribution function of the photons that are produced by this beam. And this is the second equation. And once you know the distribution function of the photons, since every photons can potentially decay to one pair, you can actually calculate at a given time how many of these photons will have produced pairs, and you have the number of pairs produced in this first generation. So to solve this problem, we can make some simplifying assumptions. And in fact, the main approximation that we are making is that for this first generation of electron, I mean the generation 0, so the initial beam, what counts is only their average energy as a function of time. So basically, we say we can approximate the distribution function of our initial beam by their number times a delta function that is centered around the average energy of the beam as it evolves with time. And to describe the evolution of the average energy, we have a well-known formula that is very good approximation that allows to calculate the average evolution by considering basically the losses due to continuum quantum emission. So it's a continuum model of radiation reaction with the Gauss correction. So this is well known and solvable. We can solve for this. And then once we have this distribution function, we can use it inside to describe the photons that are produced, and finally find directly the number of produced pairs in one generation by this formula that I'm giving here. So with probability of the photon produced by these electrons to decay and produce pairs. Okay, so this model is much simpler than all the coupled equation that we had before, and it can easily be solved because everything is known. And of course, we check this with peak simulations where you don't have to stop at a given generation. And so this is what I'm showing here. So on this side where is written model validity check, I am showing the validity of the model. So as a function of A0, the laser parameter, and gamma 0, that is the energy of the initial electron beam. So basically, how do you read this graph? All the areas where is light or white, in these areas, stopping only to the first generation works very well. So basically, for example, along this line, if I stop at the first generation, I make an error of 10%. So whenever is 1, stopping in the first generation is perfect. 1.1, it means I make an error of 10%. And even if I go on this line, I'm basically making an error of a factor of 2 in the estimate of my pairs that are produced if I stop only at the first generation. So it's a very good approximation. And as what is shown here, this rectangle is basically the parameter range where future multi-petawatt facilities will work. And so we can see that for this system in this parameter range, this approximation of stopping at the first generation and using the average energy actually works really very well. And down here also there is parameters expected for the Laxi experiment. And again, we can see that it works very, very well. So it's really a strong approximation. The difference between the top and the bottom is just the duration of the laser pulse. So in the top case, we compared with simulations for a short laser pulse like we would expect at the Apollon laser in Paris, so it's 20 femtosecond. And instead below is the longer pulse that is typical of Eli, for example, Prague, so 150 femtosecond. And again, as you can see, the white area dominates, so the model appears to be quite valid. There is also one line here, n equal 1 red. And so this is not the validity of the model, but is the line when actually the multiplicity of the particle is 1. That is, for one electron, I create one pair. So this same line is reported here on the right, is this line over here. And so what I'm showing here is the number of pairs that are produced for a single electron. So along this line, I have one pair produced for one electrons, but then if I go further up here, I have 5 pairs produced for 1 electron. And again, all this area, even if the multiplicity is larger than 1, so I have more than 1 pair produced per electron, is still enough to take into account the first generation only. So it's already taken into account by the first generation. And below, again, I show the same thing for the case of a longer duration. So I pulse at 150 femtosecond. So if in the future experimental regime, we can actually expect a multiplicity that is larger than 1. And that's kind of nice, good news for electron seeding. Okay, well, if we instead consider photon beam collisions with the laser, it turns out that we cannot stop at the first generation. I mean, we can, but we are actually able to go to the second generation of particles, and this allows us to extend our model beyond the results that we previously had. So I'm doing exactly the same game that I did before, that I explained. I start from my full equation, and then I divide into generations, and I consider the first one, second, the initial generation of photon pairs, the photons emitted by these pairs, and the second generation of pairs. Since the photon, they just disintegrate, in fact, and I start with a monoenergetic beam, the evolution of the photon distribution function is really just given by the evolution of their number. So it's this form I'm giving over here. And these you can use coupled with the other equations. And here I have the equations for the electron of the first generation distribution function, same identical equations for the positron, so I didn't write it. And there is another assumption that turns out to be important for our model, is that when I am in this regime that is relatively high probability of producing more than 1 generation, I can consider that the first generation of electron is either produced, the pairs, they're either produced with the energy of the photon or 0. So basically, it's not that I'm splitting the photon in 2, but either one pair will have almost the same energy as the initial photon and the other almost 0. So again, I can build the model based on that. So the first generation of pairs is given by this formula. And in this paper here, we already studied this, and we proposed also an analytical approximation for that, and also how to extend this to 3-dimensional model. And we call this the soft shower regime. So this we already know how to solve. But as I said, to go further, to go to the second generation, we have this extra hypothesis that the energy of the pairs produced is not evenly split between the two, but one gets all the energy and the other almost 0. So if I do that, I can then calculate the average energy of this first generation of electron and positrons in the same way as I did before. That is by assuming that the distribution function is given by the time evolution of the number of particles times the evolution of the average energy of the beam. And the equation for the average energy of the beam, again, I know how to calculate, and is given by this formula above. So if I put everything together, I have these 3 equations, basically, that lead me to the final results that is down here, where I can calculate the number of pairs produced in the second generation, if I know the first generation and the average evolution as a function of time of the first generation. Okay, again, we compare this with simulations. And again, the comparison is very good, even better than before, because the white area extends really to a large parameter space. So here, what I'm showing is the ratio of all the pairs produced over the first and second generation as function of A0, the laser parameter, and the initial beam parameter. Again, all the white area means that the ratio is roughly 1. Here it means that I make an error of 10%, and here I make an error of a factor of 2. So it means that really over a very, very large parameter space, we can predict the order of magnitude of the pairs produced very accurately. Again, as before, I'm putting the area where experiments are expected to be, either laser multi-petawatt experiment or the LPHYS experiment. And again, as before, I'm drawing the soft shower line, that is the line where we expect to have only one pair produced per initial gamma. And as you can see, part of, sometimes we will be in the soft shower regime, but we can also start to get into the real shower regime where you have more than one pair per electron. And this is also shown here, where you can...
2 minutes.
Yeah, you can see the number of pairs that are produced, the multiplicity per initial seeding particle. And again, the results are very similar to what I showed before. So we also performed, we were kind of trying to understand if there is a difference in seeding with electron or photons for an initial beam. And so we did the comparison, a direct comparison. Here we consider all generation, but of course this corresponds to our model also where it works. And in general, we can say, so this is the case of seeding with gamma with electrons, that if we are in a region where the multiplicity is not too high, seeding with gamma is more efficient. But as long as we go in a regime where the multiplicity is very high, seeding with gamma or electrons is actually the same. And we also did some comparison with previous model. So this was the model I was mentioning that inspired us. And so we improved over this model. So this is the dashed line, and this is the continuous line is our model. We did work on the soft shower limit. So now we improve over the soft shower limit. Again, this is what I've been telling you. And so I'm not going to discuss this because I took more time than I should have, but we can easily extend this problem to a three-dimensional geometry, and we did that. And we also compared with simulations. And if you have a three-dimensional geometry, what is natural to do is to calculate cross-sections. And so we can calculate cross-section with our models, and this is the black lines, and we can compare with three-dimensional peak simulation, and these are the dots. The red dots is for gamma seeding, and the blue dot is for electron seeding. And again, we can show that it works very, very well. So it's really an efficient and predictive model. So to conclude, we hope that we soon have abundant pair creation, and it means multiple pairs for one seeding particles, or a pure light scattering experiment, and we want to be able to predict how many pairs we can produce and which energies also. So we have developed a semi-analytical model that allows prediction of a very large parameter space. So I'm just summarizing the hypothesis behind this model. And just work in progress. From the understanding that we got by doing this model, we are now trying to find a simple scaling law for pair production in order to have a quick estimate of what you can expect. So thank you.
Thank you very much, Katarina, for the nice presentation. So we have time for one quick question. I don't see any raised hands.
Maybe I can ask one quick one?
Yes, please.
Maybe a very quick one. You talked about abundant pair production. And so my question is, how are you aiming to optimize it? I mean, I remember the old works from Naroshny when he looked into sort of the pulse shape of the lasers. So he sort of got a lot of enhancement of the yield by sort of, making focused pulses and so on. I mean, what are your own ideas sort of, given Apollon and you said LPHYS', so what are the three parameters you see to enhance the pair production yields? What would you give as advice?
Okay, so there are two answers to these questions. One is the fact that we don't have a lot of freedom in playing around with the parameters if we think about existing facilities.
Mm-hmm.
So we did already some work on that, and basically the free parameter you can play around is the duration of the pulse.
I've seen this.
For example, we found that you don't. Having a shorter pulse and more intense is not really useful. So you can be a bit relaxed on that. Also the other parameter is the intensity. And in that sense, also we found that again, is not necessarily the best, the highest intensity that is important to allow increase the probability, but maybe a bit larger.
Because you have less area then, right? I mean, the focal area is more.
There are not, exactly. So there are not that many free parameters to play with, and we already also looked at long duration with respect to light. But another answer is going to be given by the next talk, and it will be about really creating cascades, because the shower are limited at some point. The particles, they just stop creating pairs. But unfortunately, it's still not. There's still work in progress from the experimental point of view to get to those regimes.
Yeah, no, let's not spoil the conclusion of the next speaker.
Okay,
so let's thank Katerina, and let's welcome then Arseny Mironov for the next talk. Thank you, Katerina. Thank you again.
Thank you very much for the introduction.
Yes,
and thank you for inviting me to this conference. Actually, I'm quite happy that the conference continues its life. And I'm also grateful to my collaborators, which is Luli Tips Group, led by Katerina. And here I especially would like to commend the contribution of Anthony Mercury, who made all the simulations and a lot of analytical estimates, which I will present today. And also I am grateful to my collaborators, Alexander Fedotov and Evgeny Gelfer, who made a huge impact into what I'm going to present. So as Katerina told, pair plasma is a very desirable object in the lab conditions, because that way we could study processes that happen in astrophysical environment. And it's believed that relativistic pair plasma is responsible for generation of hard emission and gamma ray bursts or near neutron stars. But it's quite difficult to produce this plasma in lab conditions, and it will be probably very efficient to use high-intensity lasers for that. So we can produce pair plasma in interactions of such lasers with relativistic particles, for example, in showers, as Katerina presented in the previous talk. But this mechanism is limited by the input of the incident electron beam, and the multiplicity grows kind of linear with particle energy and laser intensity. Maybe this scaling is not exact, but it gives you the idea. Another option, as you know, is so-called avalanche type cascades. Is if you have a bit more sophisticated setup, for example, two colliding laser pulses, and you can seed an electron into a strong field area. This electron will be accelerated in such a way that parametric I will grow, and it will be able to emit hard photons that will create secondary particles. They will be reaccelerated, and like that you can have a multiplicity of cascades which will be exponential, and like that you can produce much more particles, as it at least estimated by theory. So thanks to Katerina, I don't have to introduce the notations and explain the basic processes. I will rely on that. And the only thing that I would like to mention is that for my talk, these two processes set two important scalings. One of them is a typical mean free pass time of electron, which you can estimate if you know the probability rate of emission. And another fact is that due to this exponential suppression, the nonlinear bright wheel pair production becomes important when a chi parameter of the photon becomes of order of 1 or higher. These coming back to avalanche type cascades, they have been simulated by many groups in past decades, and it was proved with simulations that indeed we can have plasma which can have some collective effects and even screen the laser field, and this can happen in different scenarios when you seed a few electrons or if you interact with solid targets. And it follows that in principle we need total laser intensity of order 10 to 24 if we want to start such cascades. These cascades are also interesting not just because we would have plasma, but they can they are very similar to what happens in the polar caps of neutron stars, where you have kind of similar cascades, but chi grows not for electrons but rather for photons. From theory side, of course, we don't have experiments now. There are still a lot of questions. And first of all, we would like to know what should be the conditions to start avalanche type cascades. And in principle, this first step we kind of have done with Sasha and Evgeny in this paper. But the next step would be to set some kind of scaling laws of the particle growth rates in the exponential stage, extract particle spectra and other things, but understand them analytically. And the ultimate goal would be self-consistent description of plasma. But in this talk, I will cover the second point as much as I can. I will start a bit with reminding you what kind of conditions do we need to initiate an avalanche type cascade. So imagine we have a strong laser, we put an electron inside, and the first thing that we want is that this electron is accelerated in such a way that chi parameter of electron can grow with time. Second thing that we want is that when electron emits a photon, this photon should be capable to create secondary electron-positron pair. And this is possible only if electron have enough value of chi, and the threshold value of chi would be of order of 1. And so a typical time scale of emission, chi should gain this value. And also we want this process to be repetitive so that we have lots of emissions and pair creations on the scale of the laser field. So in order to answer the question, we need to know the dynamics of particles and how chi depends on time, and it's possible to derive it for quite general type of field. And we show that chi can grow in a very specific field, which is of electric type and also time dependent or inhomogeneous. So then chi of electron should grow quadratically with time, and prefactor of this t squared depends on the field parameters, like on the local field strength and the gradient of the field. And in principle, you can calculate this for many configurations of the field, and then knowing this and knowing this requirements, we can estimate the field strength and other field parameters that we need to initiate the cascade. Just to be more concrete, let's consider a toy model, which was first studied by Fedotov and Narozhny in an old PRL paper, is rotating electric field. So let's take like pure electric fields that just rotates counterclockwise. It would represent, for example, the central electric antinode of a standing wave formed by a couple of laser pulses. For this model, we can easily calculate all the parameters needed for the model I showed on the previous slide. So we can extract, for example, the dependence of chi on time, And the limitation would be that just the field strength should be larger than critical field of strong field QD times fine structure constant. So knowing that, the authors of this paper extracted the scaling of typical lifetime of electron with respect to emission and typical scaling of energy and chi with field strength. So and the next step would be trying to understand what is the scaling of the growth rate and how this scaling compares to simulations. So that's the questions that we're studying, and so we are trying to calculate this growth rate. And I will show you a demonstration of simulations that we have, how this cascade looks like in it. So on this panel, I will show you how number of particles, particular positrons, grows with time, how average chi of these positrons changes, and this will represent a double differential distribution in energy and angle. Field starts to rotate, and we start to produce some pairs, and this is log scale, so quite fast we start producing them exponentially, and chi, or average chi, grows pretty fast, like in one period for this particular example. And then we continue producing pairs exponentially, and you see that the average value of chi kind of stabilizes around some value which is larger than 1. And also this distribution becomes also stable. It just rotates with the field, and we call this steady state. So the true exponential phase of the cascading would be the phase where you reach this steady state. Then you can extract the exponential by fitting the data, and you have your growth rate. So we did that. So this plot is dependence of growth rate on versus field strengths, and these round dots are simulations that we did with the code Smiley. And you can see that we simulated quite wide range, and this growth rate varies quite drastically from the point when you barely have pairs in several periods to a situation when you have macroscopic amount of particles in a small fraction of a period. So coming back to the model introduced in this paper, they estimated the growth rate, assuming that at very high chi of emitting electron, every photon would create a pair, and that in principle the growth rate should scale as A0 to 1/4, and this is dotted lines, this is the dot of Narozhny scaling, and we see that actually it gives an impression at what happens at super high A0, but it doesn't represent simulation results very well. So after that, in a paper by Gris Meyer, there was introduced another model was introduced, which tries to take into account that electrons actually have some kind of spectrum, and it kind of improves the result at very high A0 or very low A0. But they still rely on this paper because, for example, for high A0 regime, in this formula, they input radiation and pair creation probabilities at energies that correspond to scaling from that paper. So, but experiments that we hope to have in nearest future, they should be in this intermediate regime. So we would like to have a kind of improved model. So as a basis, we took a model of a constant rate approximation. It's different from the one that I was showing you before by the fact that the probability, the rate of pair creation and emission can be different. But this model was not very successful because in the paper, because they were taking scalings from this paper. What we did in the first place, we refined the definition of the typical emission time. Now, of course, you have to evaluate it numerically, but if you put the probability rates into this formula at this time emission, the model starts working pretty well. in low A0 and mid A0 regime, but the scaling seems somehow wrong at very high A0. And for that, we need to understand actually what happens here if we want to understand why our model doesn't work. So actually, the problem lies in the hypothesis that we assume that chi parameter of emitted photon is of the same order as chi of emitting electron. This hypothesis works very well when chi of emitting electron is of order of 1. You can clearly see it, for example, from the spectrum like this, the spectrum of emission of photons for given electrons with given chi. If chi of electron, for example, is 2, then only this small tip of the distribution would correspond to pair creation, and like this hypothesis is right. But if chi of electron is quite large, then a wide part of the spectrum contributes. But you always have photons with chi of order of 1, much larger number of photons with chi of order of 1 than these ones. And actually, this would define the most important contribution. So I skipped. So I just tell you that it actually follows from our simulations that at super high A0, this is actually what we see, is that the main contribution comes from photons that have quite low chi, even though electrons can have super high chi. So we modified the model just by saying that, okay, when we calculate the probability rate of emission and pair creation with different chi's, and we set the chi of photon to be like minimum between 1 or chi of electron. And then this purple line is this improved part of a model where we should consider chi of photon to be 1, and it fits the data super well. So I'm kind of tight on schedule, so I would like to go to the nicer section. So the previous model was very nice, but it's 2D. The real case would be, of course, 3D. For example, if we consider standing wave formed by a couple of circularly polarized laser pulses, then the model would be like this red line on this distribution of electric nodes and antinodes. And based on the analytical models that we derived before, we can tell that cascading can happen only in electric antinodes, because in magnetic antinodes you have magnetic type fields and you don't accelerate particles in a good way. But the 3D effect that you observe is that even if you seed particles in this optimal place, secondary electrons and positrons will start migrating to these gray areas. And this should kind of a bit reduce growth rates. So we defined so-called migration rate as a typical time of this migration. We perform like simulations, like 3D simulations, in order to study like the effect of this migration. So this is kind of same plot, but orange squares is a simulation in a standing wave. And you see that for lower A0 compared to the circles, we see indeed the suppression, like we have less particles. And we could manage to stick this migration rates into our model, and it works like perfectly well, like a gem. Like this production is exactly explained by migration. So what was at first surprising to us is that at very high A0, actually everything starts to coincide with a 2D case, but then we make some analysis, and you just see that when the rate of pair creation and emission becomes much larger than migration rate, cascading happens like in a plane. And we have like 2D model like working perfectly well for high A0.
Yeah, 2 minutes, please.
Thanks. So Another example of realistic field is, for example, very tightly focused laser pulse. And we showed in this paper that, like in principle, if you have extremely high intensities, you can have cascading like that. But these laser pulses, as they are tightly focused, they can have different configuration of field. And for example, you can make so-called E-type fields. Okay, here I must explain that due to tight focusing, you can always have some kind of longitudinal field. And so for E-type fields, you will have like B fields, which are longitudinal, but E fields will be transverse and they will be higher than B. And that's why you will be always able to accelerate electrons so that chi grows. And we show that, yes, you can have cascading in this case. But you can take another laser pulse, which has exactly the same intensity profile, but you have electric field, which is longitudinal, and B, which is transverse. And it appears that in this field, you don't have acceleration in the way you want, like chi doesn't grow for many periods. And you don't have cascading, even though you can have a very high intensity, like the same intensity. So just one more thing is that since we have this nicely working model of a growth rate, now we can estimate when plasma effects become important. So here we plot like typical time at which, for example, this orange curve, typical time at which you can start screening versus A0. And like orange curve is our model prediction and squares is a simulation result, and we can see that it works quite well actually. So since I'm running out of time, I'm going to my conclusions. So we introduce a nicely working model. Publication is like the manuscript is still in progress, so we hope to submit it soon. And also another point is that understanding the structure of the field is really critically important if you want to understand whether you will have cascade or not. So we will need kind of diagnostics of the field type, of the, like what field type do we have for a given laser. So last thing is that I would like to advertise a SMILEY workshop that will take place in Prague in November this year. So please apply if you would like to learn how to use SMILEY. And thank you for your attention. I would like.
Hey, thank you. Thank you very much for the nice presentation. So we have again time for a very quick question or comment. I can make one quick question or comment. So if you try to understand what would be the impact of slight changes on the laser profile,
you mean this?
as you mentioned, yeah, but the laser these high intensity lasers on focus, I mean, they are very far from what we usually, we in the sense of theoreticians or simulationists assume in our, is this something that now you can test, have some kind of an analysis of the dependency on the aberrations or other effects on the beams?
So I would say like the following, like once we have the distribution of the field, like exact, like magnetic and electric, yes, we can just take the models that I introduced, like in the very first slides, like this model. We can calculate everything. It's just a technical calculation and say, how much will we have cascade or not? Like at least this one we can tell for sure. The only problem is that when you go to an experimentalist and ask him, can you give me the exact profile that you have and give me the type of the field you have, they say that usually they don't control it very well and they don't know every detail like of the laser pulse. But
they can provide the aberrations of the system, laser front deviations, and so it's nice that you have a model now that can account for that. Yes.
Yeah. So in principle, like you just give the field distribution like electric and magnetic, and then we stick it into the model, and it should work in principle. Not for the growth rate yet, but at least to say whether we have the cascade.
Okay, perfect. Okay, that's great. So thank you so much. We need to move because we are we're a little bit already behind time. And so our next speaker, I think, is already ready. Suo Tang is going to give the next presentation, which is a 15-minute presentation, and is going to talk about plasma harmonic generation for highly efficient bright Wheeler pair creation. Yes, please, okay. Please go ahead. Thank you.
Okay, thank you. Thanks the organizers for this invitation. My presentation is about plasma harmonic generation for highly efficient bright Wheeler pair creation. Can you hear me? Yeah, okay, thank you. Thank you, Christoph. As we know, the detection of efficient bright Wheeler pair creation is one of the main goals for the modern day laser particle experiments, such as LPHYS' E320 or S9 campaign. One of the potential experimental model is to collect a beam of high energy photon with an intense laser pulse. The yield of this laser photon collision model depends mainly on two factors. One is the quantum parameter, I call it the eta, which characterizes the center of mass energy in the collision. Here, K is the laser wave vector, and the L is the photon momentum. If eta smaller than 2, that means you need more than one laser photon for the creation process, and only non-linear process is possible. If you want to open the channel for linear process, then you have to make eta larger than 2. The other factor is the laser intensity, is the normalized laser intensity factor, which characterizes the nonlinearity of the creation. So if you want to increase the creation yield, then you can either increase the energy parameter or the laser intensity. The generation of ultra-intense laser pulse would be feasible in the future, but as you know, this would be very, very expensive. Here we introduce a low cost, but still very effective way to significantly enhance the creation yield with the currently available parameters. Here, this is the sketch for our proposal. We use a G-wave photon beam collected with the plasma reflected pulse from a linearly polarized laser pulse, which harmonics will be included in this reflected pulse. Here I show a comparison between the incident and the reflected pulse based on a 2D peak simulation with these parameters. As you can see, compared with the incident pulse, the blue solid line, the amplitude of the reflected pulse is effectively magnified. You can see here, and more importantly, which held harmonics are superposed in the reflected pulse. You can see here. These high order harmonics will be very important for pair creation. And the other main feature of the plasma reflected pulse is the evident field asymmetry, as you can see here. When you consider this oblique incidence, this evident field asymmetry will effectively polarize the created particles. The plasma harmonic generation has been reviewed in this paper. If you want to know the details about the plasma harmonic generation, you can look into this paper. Okay, so before we go to the numerical results, I want to highlight a few points. First one is we focus on the currently available parameters of weakly focused laser pulse with the intermediate intensity are used to irradiate an overdensed plasma, and then collide nearly head-on with a G-wave photon beam. So with these parameters, the contribution from the high frequency component would be very important as it can significantly increase the energy parameter. So this differs our research from the previous work in which plasma harmonic are also proposed to intensify the QED phenomenon. But in this work, the high order harmonics would not contribute to the QED effect directly, but people use the convergence effect of the high order harmonic to get a super intense field. In our work, we make the high order harmonic in the other direction to increase the increase this collisional energy parameter. So to consider this high frequency contribution, for QED calculation must be performed. The widely used LCFA would not sufficient. Okay, to simplify the calculation, we use plane wave approximation as the head-on collision geometry is considered here. So the particles transport movements should be much smaller than the scale of the field transport variation. And the other reason for this plane wave approximation is the angular spread of the generated harmonic is very narrow. Here, I show the distribution of the harmonic wave vector. As you can see, the spread of the transverse wave vector is much smaller than the value of the longitudinal one. So the angular spread of the generated harmonic is very narrow. In my case, it's smaller than 20 million radian. This result match quantitatively with the recent experimental results. Of course, if you want to consider a tightly fluxed pulse, then you need to consider the method introduced in this paper. Okay, so with this point in mind, then we start from the S-matrix method and then get the position spectrum. I think this is quite standard of form for the position spectrum. Here, alpha is the fine structure constant and S is the fraction of the net front momentum taken by the position from the incident photon. And this is the window average of the field. We also give the position spin in this form, which is polarized in the direction of the magnetic field. As you can see, this spin depends on the field asymmetry. Okay, if you have a symmetric field, the positive part and the negative part, then the window average of the field will be 0. Then the field will be unpolarized. So if you want to polarize the particles, then the field has to be asymmetry. Okay, the derivation of these equations can be found in our recent paper. Okay, now we look at the numerical result. Here I show the comparison between the position spectra obtained from the high energy photons in the head-on collision with the incident and the reflected field at the pulse center. So compared to the pair creation in the incident pulse, the spectra, this solid line, the spectra in the reflected pulse in this solid line is much higher and decays much slower than that in the incident pulse. That means the creation yield in the reflected pulse is significantly enhanced. For 10 GeV photon, see the blue and the green line, the enhancement is about 30 times, and for the 5 GeV photon, you can see the red and the black dashed line, the enhancement is more than 3 orders of magnitude. We also show the calculation with the change of the transverse misalignments. As you can see, the pair creation is not only significantly enhanced at the pulse center, but also very effective at a much broader range than the incident case. So to understand how this yield enhancement obtained in the plasma reflect pulse, we plot the position spectra created by the different frequency component in the reflect pulse. Here we consider a 10 GeV photon, and then the corresponding energy parameter is 0.12. The transverse misalignment is arbitrary. We choose this value. So we first calculate the positions created by the frequency components smaller than this critical value. That means only nonlinear Bragg-Wiener process is possible. You can see this blue dashed line. And then we calculate the pair production from the higher frequency components. And then for them, the linear Bragg-Wiener process is possible. See this blue dotted line. As you can see, the nonlinear Bragg-Wiener parts determines the height of the spectrum, and the linear breadwinner process result in this slower spectral decay. And both this nonlinear and the linear production yield much larger than the obtained in the incident pulse. So that means the research harmonic in the plasma reflected pulse can not only improve the yield of the nonlinear breadwinner process, but also open an effective channel for the linear breadwinner process, which is forbidden in the incident pulse. Okay, here we show the comparison between the nonlinear breadwinner process and the linear process with the change of the transport misalignment. So you can see as the pulse center, the nonlinear breadwinner process is dominant, and the linear breadwinner process extends the effective creation to a much broader transport range. Okay, here we also consider the robustness of our consideration. So you can see here for a very broad, there's the incident angle and the plasma pre-gradient and the plasma density material. So for all of these parameters, you can see the particle yield in the reflected pulse is much larger than that in the incident pulse. But when you consider the higher this intensity and the larger photon energy, the level of the yield enhancement become smaller, but it's still very significant for the currently available parameters. You can see for the laser intensity equal to 5, the yield for 5 GeV case is improved more than 40 times, and for 10 GeV case, the yield is improved more than 6 times. We also consider 2 potential photon sources for the laser particle experiment. One is the Compton photon source, the other one is the brimstone. Both are generated by the 60.5 GeV electron. For the Compton photon source, it's collected with the laser pulse, and then for brimstone, this electron collected with the gold target. Here in the left figure, the magenta dotted line is the photon spectrum. So then with this spectrum, you collect with the incident and the plasma reflected pulse. You can see the enhancement is also significant, more than 1 order of magnitude. So for
2 minutes.
Okay, thank you. Almost finished. For Compton photon source, the enhancement is 21 times, and for brimstone is 11 times. And then we also look at the spin polarization of the created position. You can see because of this evident field asymmetry, the created positions are highly polarized with the peak value larger than 80%. And because most of the electrons are produced around S equal to 0.5, then total polarization of the positions, the total polarization of the position is around 60. So here I also want to point out the position spin, the polarization of the spin depends on the field asymmetry, and the asymmetry is controlled by the laser incident angle. So that means for our case, the position spin polarization can be simply controlled by just adjusting the laser incidence. Okay, then we move to the summary. We detail the exploration of the breadwinner pair creation using the plasma generated harmonics. Our proposal could be realized in the modern day in the upcoming experiment and can be used as a robust scheme to generate brilliant and highly polarized position beam. The rich harmonics in the plasma reflected pulse can not only improve the yield of the nonlinear process, but also open an effective channel for the linear process. In the currently available range, parameter range, the yield can be improved by more than 1 order of magnitude. All my presentation can be found in our recent paper. Thank you for your attention.
Okay, thank you very much. Thank you very much for a nice presentation and very, very detailed presentation. We have time for one quick question, one quick answer. Yeah, Christoph, please.
Maybe quick, very, very interesting work. So just a quick thing, you mentioned the locally constant field approximation cannot be applied. Did you compare with calculations within this approximation to see that, or is just there? I mean, you are in a rather extreme parameter regime, right? So,
no, I do not. No, I just use the plane wave approximation, because if you want to use the method in this paper, the calculation is too expensive.
Oh, I see. That's okay. Okay, thank you very much. Very interesting.
Thank you very much. So now we need to move to our next speaker. So let's thank Swo again. And the next speaker is Alexander McLeod.
Hi.
Yes.
Can you hear me okay?
Yeah, we can hear you. Can you share your slides?
Yes. Yeah.
Let me start. You have 15 minutes. So.
Okay, can you see my slides?
Yes, we can. Yes,
perfect.
please.
Okay,
please.
thank you.
Please.
Okay, so
Alexander is going to talk about all optical nonlinear Bright-Wheeler pair production with high power lasers. So thank you for being here.
Okay, thanks very much. So thank you for the opportunity to present this work. I'm Alexander McLeod from the Eli Beamlines facility just outside of Prague in the Czech Republic. So this work was a collaboration between myself and my Eli Beamlines colleagues, and details can be found in this PRA paper which we published just earlier this year. Okay, so I'll talk about three things. I'll talk about photon sources for nonlinear Bright-Wheeler pair production experiments. I'll talk about the simulations that our group has been doing on the gamma flash photon production mechanism. And then I'll finish off by talking about using those gamma flash photons for nonlinear Bright-Wheeler pair production studies. Okay, so photon sources. So we've had a lot of introduction about the nonlinear Bright-Wheeler pair production process, so I don't need to go into too many details. The main thing, though, is that we're going to be, in this talk, focusing on the fully non-perturbative strong field regime. So this is the regime where your intensity parameter is much greater than 1, and that means that you're absorbing a large number of photons from the background field, and you need to include the background field non-perturbatively in your calculations. So this is a regime that I'm going to be working in. So if we can use lasers essentially as the source of the electromagnetic fields, we still need to worry about where our photons are going to come from to interact with those lasers. And we have a few requirements on those photon sources. The main one being that we need very high energy photons for the sort of available laser intensities that we're going to have now and in the near future, namely within the MeV to GeV range for the energy. We also need a large number of those photons because the number of pairs that we can produce is going to be directly proportional to the number of photons which are incident on our laser pulse. We would ideally like to be able to synchronize up our photon source with our secondary laser pulse for the interaction to happen, so that we've got good overlap between the beams, for example. And ideally, we would like an efficient process for generating these photons so that we're not wasting too much energy and as a result of that, money for running these sorts of experiments. So the options available to us are essentially either electron-seeded photon sources or laser-driven photon sources. And today I'm going to be focusing on the laser-driven photon sources for this talk. Okay, so laser-driven photon generation, as it sounds, we use a laser pulse to generate these photons, and we do that by irradiating typically a solid target, so a metallic target. Throughout this talk, I'm going to be focusing on lithium, but you can use other materials as well. Some of the advantages to this photon generation scheme is that it only, in principle, requires a single stage to produce your gamma photons. You produce large numbers of the gamma photons in the MeV to GeV range, and the conversion efficiency has been shown in several studies, highlighted in this plot on the right-hand side, which is taken from the review by Gnoskov et al. The conversion efficiency can be tens of percent, maybe up to 100% if you have some multi-beam configurations. But in the single beam configuration, you're looking at a few tens of percent conversion efficiency between the laser energy and your photon energy. So with this sort of scheme, we would also hope that it could be easily synchronized with a secondary pulse because of this fact that we've only got a single stage involved. So this is the type of scenario that we're going to look at. And to study nonlinear bright Wheeler pair production, we imagine this sort of experimental setup where we have two stages, essentially. One, which is going to generate photons via this gamma flash mechanism, and the second stage, which will collide a secondary laser pulse with the produced photons to produce electron-positron pairs. So the key physical parameter at any laser facility, which is sort of the limiting factor, is going to be the total available laser energy that we have at the facility. So we can imagine splitting this total laser energy into two pulses, E flash, which is going to be the energy of the driving laser pulse, which produces the gamma photons through the gamma flash mechanism, and the second E pairs, which is going to be this the energy of this counter-propagating pulse, which then collides with the photons to produce the electron-positron pairs. Okay, so that's the scenario that we're going to look at. So first of all, we need to know the properties of the gamma flash photons that we're producing. And our group at Eli Beamlines has done a lot of work on this topic. And throughout this work, I'm going to be using spectra, which we have in great detail in this talk by my colleague. So essentially, we're using a lithium target with 12 micron diameter and 10 micron thickness. We're going to irradiate that target with a long nanosecond duration pre-pulse, and then send in a main pulse afterwards. So the pre-pulse basically creates this channel, which when we send in our main pulse, leads to an intensity enhancement of the field, and that leads to a slight increase, or in some cases significant increase, in the production of photons within the material. So that data basically gets used as an input for our 3D PIC simulations to generate the photon spectra, and the intensity, the radiant intensity of the photons is given in this plot here, and this is using a 17 femtosecond duration laser, when Thai sapphire laser focused down to a beam waist of 1.86 microns. And essentially, because we're using a linearly polarized laser pulse, we get this double lobe structure appearing in the radiant intensity. So the idea would then be, we want to find the sort of the maximum area within this radiant intensity and focus down a secondary laser pulse into that region and see if we can produce electron-positron pairs using those gamma photons. So if we take a line out of the intensity plot that I just showed, so across one of these lobes, then we get something like the left-hand plot here, plot A, and we're showing this for a range of different powers of the incident laser pulse, so 5 petawatt, 15 petawatt, and 50 petawatt, corresponding to sort of current and next generation laser facilities. Obviously though, our photons, not all of these photons are going to reach our secondary laser pulse some distance away from the target. And so we're only going to focus on the photons within the peak, which are these shaded regions in this plot. In terms of the energy spectra shown on the right, the darker coloured lines is the energy spectra of the sort of full angular emission of the photons, and the lighter coloured lines are just these shaded regions in the left-hand plot. So you can see that we're capturing most of the highest energy photons in the spectra, and we're losing out on mainly lower energy photons in the interaction. So these are the photons that are going to use for nonlinear bright Wheeler pair production. So just so about our colliding laser then, so the secondary laser which is going to collide with these photons, we're going to approximate it using plane wave model with a Gaussian temporal envelope. And because we're using a plane wave, we can't focus our laser pulse too much. but you can come up with a sort of order of magnitude estimate for the limit of the beam waste that we can use. And if we use a 17 femtosecond duration Ti-Sapphire laser, then it should be reasonable to neglect these higher order focusing effects if we choose a beam waste of about 2.5 microns. So that's what we're going to use. Okay, so to calculate the total number of pairs, this is pretty standard. We have the area of our colliding laser pulse, which is just given by the square of the beam waste. We imagine that, or we can approximate the photons as essentially propagating from the target rear surface as a roughly uniform flat disk with some distance d to the laser focal spot. And then we just calculate the sort of geometrical factor of the number of photons and plug that into our LCFA probabilities to get the total number of pairs out that we can expect. So we have the sort of the geometrical factor, we're integrating over the photon spectra, and we have this probability weight calculated in the LCFA. Okay, so before going on to the results, just a summary of the laser parameters. In each case, we're using a 17 femtosecond duration laser pulse of a Ti-Sapphire wavelength. But we're focusing the driving laser pulse down slightly more because we're including the focusing effects on the target, but we're not as strongly focusing for the colliding laser pulse, just so we can get an estimates using the plane wave approximation. So we'll consider three different cases corresponding essentially to a 10 petawatt class laser system, a 30 petawatt class laser system, and a 100 petawatt class laser system. And then within that, we'll also consider different ratios of the amount of energy that we're putting into the gamma flash production part and the electron-positron pair production part. Okay, so these are the sorts of results that we get. So this shows the total number of pairs per shot that we could expect as a function of the photon propagation distance. So this is the distance between the photon source at the rear of the rear surface of the target and the secondary laser pulse's focal spot. And we can see that in each case that we've considered, the optimal splitting of this ratio between the photon generating part and the pair production part is 1. So where we equally partition the available laser pulse energy into these two branches of the setup. And if we take that optimal configuration and we consider just a nominal distance d of about 10 centimeters away from the target, then we could expect on the order of sort of 0.01 pairs per shot for a 10 petawatt class laser system, going up to about 1,000 pairs per shot for the 10 petawatt class laser system. And at 0.1 hertz, this corresponds to say roughly 5 pairs per hour for the 10 petawatt class system, going up to about 10 to the 5 pairs per hour for the 100 petawatt class system. Okay, so in our paper, we also have more details about things like the angular spectra and the energy spectra, but that's all that I'm going to present today. But there are some future optimizations that we would like to do. Namely, we would like to investigate sort of optimizing the laser pulses to try and increase the yield. So this will be things like looking at different laser polarizations of the driving laser. Some work by my colleague looked at, for example, radially polarized laser pulses and found that that can lead to a much higher collimation of the photon beam, which you produce from your target. There was also the talk on Tuesday, which looked at including alternative field configurations, like including a magnetic field, and showed that that can lead to 2 to 3 times increase in the number of high energy photons. And we also want to look at optimizing for the pulse durations of both the driving and colliding laser pulses. Okay, so just to summarize, we've been looking at nonlinear Brightweight pair production, which requires large numbers of MEV to GeV photons. The gamma flash photon mechanism can be one such method of producing those photons, and we've shown that it could be feasible to use this approach in a very simple experimental setup, just involving essentially 2 stages for our pair production scheme. So details can be found in this paper, and I thank you all for your attention.
Okay, thank you very much, and thank you for keeping up the time for the presentation. We still have a couple of minutes for questions. I have one question regarding, so how close to the real description of the beams have you considered for the scattering beam on the gammas? So you generate the gammas out of the peak simulations,
yes,
and then they scatter off the laser pulse, right?
Yes.
Have you assumed a Gaussian laser pulse or with different properties, or it's strictly a plane wave type of approximation?
For the secondary laser pulse, the one which is colliding.
Yes, exactly.
Yes. So in this, we've used the plane wave just to describe that, but sort of with a finite transverse size.
Oh, okay.
So essentially, just considering the sort of very center, or around about the very center of a focused beam.
Mm-hmm.
We've not focused it down too much, so that hopefully these focusing effects are sort of higher order, at least an order of magnitude smaller. But this is something that we want to look at in more detail. So looking at proper focusing with the secondary laser pulse, looking at a more realistic, maybe finite size for the photon beam, these sorts of things. So these sort of optimization problems. Yeah.
Yes, very, very interesting. Yeah. Okay. Thank you very much. We need to move to our next. Oh, there's one last question. Arseny has a very quick question, or?
Oh, yes. Yeah.
Okay, so thanks for the talk. I just have a small question. For your distribution of photons that you get after interaction with a solid target, how controllable is the shape of the photons, for example, in terms of angular distribution, or it's kind of fixed for you cannot really control it with the input laser?
So if it's a very difficult problem trying to get this sort of control over the spread of them. For these linear pulses, you basically get this sort of double lobe structure appearing, where most of the high energy photons are almost on the laser axis. So assuming you have sort of a head-on 90-degree incidence angle with your laser pulse. But as I said, we're wanting to look at other things like other polarizations for the laser pulse, this sort of thing, to hopefully optimize the directionality and get more control over that in future.
Okay. Thank you very much. So we need to move to our next speaker, which is Ivan Alexandrov. I think Ivan already tested his presentation. So Ivan, welcome. You can start by sharing your slides. You have 15 minutes, and you are going to talk about Schwinger pair production, fast switch-off effects versus dynamical assistance. Please.
Thank you for the introduction. Can you hear my slides?
Yeah, we can see them and we can hear you very clearly. Thank you.
Okay, thank you. I would also like to thank the organizers of this conference and this seminar in particular. And today I'm happy to give a talk on the pair production process in rapidly varying electric fields. Namely, I will speak about the 2 interesting effects mentioned in the title of this presentation. This is the plan of my talk. After a short introduction, I'm going to describe what the dynamically assisted Schwinger effect is and what we mean by the fast switch-off effects. Then we will discuss the relation between these 2 effects and briefly assess the experimental prospects of these 2 scenarios. The talk is based essentially on our manuscript, recent manuscript, which is now considerably modified and extended and will be very soon updated on the archive. I would also like to thank our referees who helped us to improve the paper. So we are speaking about the phenomenon of electron positron pair production in the presence of strong external backgrounds. And a simple illustration of this process can be obtained if one formally introduces the potential energy of the Dirac particle in a static and uniform field. So the electron in the negative energy continuum can tunnel into the positive one. So we will have a real electron, and the hole in the energy negative continuum will be interpreted as a positron. And we can estimate the probability of this process, of this tunneling process, and it is suppressed for small e and reflects non-perturbative nature, and it cannot be expanded in any series in terms of e. So as we know, the probability has this form, where EC is a critical or Schwinger field strength, which is a very large value, which cannot be reached by means of the modern laser facilities. On the other hand, I'd like to mention two important points that must be taken into account here. First, we know that the pair production probability contains also a pre-exponential factor, which involves the spatio-temporal volume of the external field in units of the Compton wavelength. And since the realistic laser fields have macroscopic wavelength on the level of 1 micrometer, this prefactor is huge. Second, it turns out that the temporal dependence of the electric field also enhances the particle yield, and in this context, a very important parameter is the so-called Keldysh parameter, which is a dimensionless ratio of the field frequency and its amplitude. It turns out that this parameter allows one to distinguish between the following two regimes. When it is much less than 1, we have a slowly varying strong background, and the pair production probability is suppressed by this exponential function, by the Schwinger exponential function. This is the so-called tunneling or Schwinger regime. And if the Keldysh parameter is very large, one can simply use perturbation theory and obtain this result in the so-called multiphoton regime. We are interested in the first domain, as it is non-perturbative, and the corresponding physical effect has never been observed experimentally. So taking into account these two aspects, we can conclude that the actual threshold of pair production is not the critical field strength, but in fact it is 1 order of magnitude smaller, which corresponds to the peak intensity of 10 to the power of 27 approximately, which is still very, very large, because it is about 4 orders of magnitude higher than the intensity that can be obtained nowadays. So in this talk, I'd like to discuss the 2 mechanisms that can be used to enhance the number of particles and thus lower the pair production threshold. So let me first discuss them separately, and then we will try to compare them and identify the relation between them. So the main idea of the so-called dynamically assisted Schwinger effect is based on adding a second pulse weak and rapidly varying pulse, which should assist the pair production process in the strong and slowly varying background. So the corresponding Keldysh parameters are small and large respectively, and it turns out that the particle yield can be substantially enhanced due to the following mechanism. When we have an additional rapid pulse, the electron can be lifted by absorbing a high energy photon. So the tunneling distance gets shortened, and accordingly we obtain this additional factor, which indicates the exponential enhancement of the process. The key parameter here is the ratio of the high frequency omega and large field strength, which is called the combined Keldysh parameter. Speaking a bit more specifically, as was demonstrated in this paper where this mechanism was proposed, we can consider this simple configuration, which is a combination of two Zauter pulses. And it turns out that if we start to increase the frequency of the second pulse, then at a certain value of the combined Keldysh parameter, the particle yield will be drastically enhanced. So let me provide some examples of the momentum distributions. In this slide, we display a momentum distribution in the case of an individual strong pulse, where the numbers indicate how many photons from the external field should be absorbed, and these numbers can be identified by means of the energy momentum conservation law, taking into account the effective mass shift. In this example, the strong field is not a Zauter pulse, but it's an oscillating background, but this doesn't change the idea of the enhancement mechanism, so it's not that important. In the presence of a weak pulse only, we have this momentum spectrum, and the Pair-Production probabilities are very small because the amplitude of this weak, rapidly varying pulse is very small. But if we combine the two pulses, the first one and the second one, then we obtain the following momentum distribution, which is essentially the same as that I showed you first, but the Pair-Production probabilities are indeed enhanced. So next, let me describe what fast switching effect is. As we know, in many theoretical approaches, one evolved the so-called adiabatic number density of particles, which can be interpreted as a physical number of pairs only at asymptotic times. At intermediate times, this distribution function is ambiguous and may have very large values. So this can be illustrated, for example, by this graph, where we clearly see that the adiabatic number of pairs can be several orders of magnitude larger than the final number of pairs. The question is whether we can take advantage of this effect. First of all, we know that the adiabatic particle number is evaluated at intermediate times is the number of physical pairs which we would measure if the external field was suddenly turned off at this time instant. It suggests that one can try to enhance the final number of pairs by properly shaping the external field profile and introducing a smooth by sufficiently rapid switch-off function in the vicinity of T star, which corresponds to the maximum value of the adiabatic number of particles. So this idea definitely works, but it is not that clear to which extent one has to reduce the switching time tau, and it is also not clear whether we can indeed lower the Pair-Production threshold within realistic experimental setups. It is also very interesting to identify the relation between this effect and the dynamically assisted trigger effect. So these were the goals of our study. So let me briefly discuss our investigation and share our findings with you. So we studied two simple field configurations modeling the two effects under consideration. First, we used a simple combination of two Zauter pulses. The weak pulse with a small duration can be seen here in the vicinity of the origin. And the second field profile represents a rectangular with smooth switching parts of duration tau and cosine squared profile. As we already discussed, we know that in the case of the dynamically assisted trigger effect, the Pair-Production enhancement occurs when the combined Keldysh parameter is no longer small. So the question now is how short should be the switch-off parts in the second mechanism for the particle number to significantly increase? Well, the answer is exactly the same. So the onset of the enhancement is given by the same condition, but of course the minimum of this parameter tau is different. And this means that the two mechanisms are indeed very similar. This was found by means of our numerical computations based on the quantum kinetic equations, and I think most important, by means of the Wolfline instanton approach, which allowed us to deduce this condition analytically. So let us now employ this condition to estimate the enhancement threshold in terms of the laser wavelength. So in this table, we present the wavelength, which is assumed to be twice larger than the parameter tau for different values of the field amplitude. We observe that all of these values are very small. They are much smaller than the typical laser wavelength, which is of the order of 1 micrometer. And it means that shaping the field profile and switching the external field on such a small scale seems unrealistic, unfortunately. It means that, but on the other hand, the dynamically assisted Schwinger effect seems feasible because the weak rapidly varying field component can be introduced by means of a high frequency photon. It doesn't necessarily need to be a laser pulse with wavelength of 1 micrometer.
Mm-hmm. Yeah, 2 minutes, please.
Okay.
Perfect.
So yeah, here I present the main conclusions. I would like to point out that the wavelength of 10 to the power of minus 6 micrometer corresponds to the photon energy approximately 1 MeV. So if we consider the combination of a strong laser background with a large wavelength and an additional radiation with this photon energy, then this setup seems to be indeed realistic, although the second mechanism of the pair production enhancement is likely to be not that promising. Thank you for your attention.
Okay, thank you very much, and thank you very much for being on time. So we have time for one quick question. Yeah, Christoph, please.
Yeah, maybe a quick one. I mean, very interesting ideas to enhance the pair production. As far as understood, you have treated the laser field by the electric field. Is there any chance that you could introduce into your model the magnetic field, sort of at least to first order when you sort of consider you are at a node where of crossed fields where the magnetic fields are small, right? Is there any chance to do that? To include this, yes, or is it too complicated?
We can introduce also a spatial dependence. At least we can let this field configuration depend also on one spatial coordinate. So in principle, we can consider something like a standing wave, for example, with a certain spatial profile. And in this case, of course, we will have also magnetic field. But the idea was first to analyze the simplest configurations in order to understand different mechanisms.
But I think it's the next step, right? Because naturally there's a magnetic field in the laser field, right?
Yeah, this should be more, considering more realistic, the grounds should be the next step, yes.
Okay.
It's also very interesting.
So it's realistic to do that. Super, thank you.
Yeah. Thank you.
Okay, thank you very much for your presentation. Very nice. So now we move to the last talk that is going to be given by Deepak Shah. I'm very sorry that I could not keep the other speakers in time, and so we are a little bit late. But we are looking forward. We are looking forward to your talk. So if you could share your screen, we would be happy. Yes, we can hear you. To hear your talk on the finite time behavior of vacuum instability. So can you share your slides? Yes. Okay. Here we go.
Yes. My slide is visible.
Yes. So whenever you're ready, we can start for your 10-minute slot.
Okay. We can start. Okay. Myself, Deepak, pursuing my PhD at Rajaramana Center, LPHYS' 23 National Institute. Can I audible?
Yeah, well, we can't hear you very well, so maybe you need to be getting a little bit closer to the microphone, probably.
Okay. Now it's fine.
Yeah, I think it's better, but let's give it a try.
Okay. First, I acknowledge the organizing committee of Laser Physics Workshop for giving this opportunity to present my work on finite time behavior of vacuum stability, in which we try to study the behavior of vacuum at finite time using the particle distribution function. And the outline of the talk is that first we introduce the concept of Springer mechanism, in which the particle production through electric field, and we theoretically description for the formation of pair production, and result which is basically motivated by the calculation of the distribution function at finite time, and we conclude in summary. In Sauter Sugar mechanism in 2031, Sauter using the Dirac theory, and they comes with the formula for creation of the electron position at a sufficient electric field, and they say in tunneling picture when have Dirac theory, according to which that negative energy state and positive energy state, when we if have enough electric field, that negative from negative energy state, that electron that are virtually shift to the positive energy state, and the tunneling probability is defined by this formula, and where this is a critical field, which is very well established phenomena. And in 1956, Heisenberg Euler drive the integral representation for one loop effective Lagrangian, and using that imaginary part of that vacuum decay rate is calculated by Schwinger in 1951. They calculated the similar formula as the sort of calculated, and the corresponding corrective field limit is properly known as the Schwinger limit, and which is 10 power 16. That is very huge. That from this equation, this is shows the exponential suppression and turning effect, and this is also that non-perturbative. We not solve is under the perturbation theory. So non-perturbatively, it is find the interesting physics that is not unexplored for QED region, and corresponding to that electric field strength, the intensity is 10 power 29 is required, and this is a constant field approximation. Give rough estimate. Peoples and researchers and scientists are in several years trying to reach this goal using the time, space, and time dependent electromagnetic field, and study its behavior depending on the temporal spatial structure, and seeing that momentum spectrum and effect of electromagnetic field in stability and secondary effect. There many experiments are planned around the world. The Hercules laser in USA reached the intensity around 10^22, and many laser facilities are planned in the future to reach to this goal. Theoretical description in this we mainly describe description of the electron position in electric field. We only have QD Lagrangian and Dirac equation, and using that we can try to find out that. Here we see vector potential that we are considering is only time dependent, and the experimentally this situation is achieved in the focal spot of 2 or 4 quantum propagating laser, where the electric field is homogeneous in space due to the spatial frequency scale is much larger than quantum wavelength. And we choose in z direction for the mathematical purpose, and the very strong field, due to the very strong field, we consider as a classical electric field treated as a classical, and many field of approximation we not taking the background field and vibration effect. And next, the Dirac field is constructed using that single particle solution or spinor function for time in presence of time dependent electric field, and corresponding that mode function satisfies the oscillator type equation. There is oscillator type differential equation. Solving this, the positive and negative energy state, and no clear interpretation of particle antiparticle is possible. And we see in Hamiltonian there is some non-meshing of diagonal elements, and to diagonalize the Hamiltonian, we need to change the basis for creation and relation operator, which is achieved by Vogel transformation. Switching to the quasi-particle picture, we define the creation and relation operator that now depend on time, and using that we define the single particle distribution function. Since the single particle distribution function gives the most complete description of vacuum pair creation from in state to the out state, and it gives the distribution in momentum space as dependent on momentum and time dependent quantity. It's defined see the from initial equilibrium state to the final equilibrium through saying the intermediate state, also possible to study the vacuum state. And we interpret only electron position distribution for plus minus infinity. We mainly focus in that we are not practically possible to reach to infinity time, and we point out that there at finite time maybe we can see the electron position pairs, which we discuss in result section. Now, for this work, we consider the sorter pulse field, and the corresponding vector potential is that main thing is that we chosen the field strength as a 0.2 of that critical field, and the tau is 10, and which is a sorter pulse. And we see that after some 2 tau, the electric field is nearly vanished. After that, we maybe see the distribution function at 2 tau, which is gives the electroposition distribution function. Next, in result section, we using that sorter pulse, we find out the exact solution for the mod function using the Dirac equation that we previously written, and using that we calculate the Vogel transformation function. In calculating the exact differential equation, we change the time variable to easily solve the differential equation as a hypergeometric differential equation, which is a well-known result. And using that differential equation solution, we find out the Vogel transformation coefficient, which is related to distribution function. And we find out that distribution function depend on some hypergeometric function F1 and F2 and some parameter of omega, which is a quasi-particle energy that we define in previous slides, and some electric field and that vector potential parameters. So now, for understanding the dynamical behavior of distribution function, the time evolution of distribution function of shows that the virtual electron positron plasma in early times passes through 3 different stages. First is QPP, quasi-particle electron plasma stage, transient stage, and REPP stage. In initial QPP to final REPP stage, distinguished by this fast oscillating structure, which is the transient stage. It is where we some mark the time T in to T out, that initial and final time of transient state. And at QPP stage, the particles are at off cell configuration, passing, and through transient state, particles tries to reach are on cell condition by supplying energy from electric field, taking energy from electric field and reaches to on cell condition at RPP region. That oscillation, that rapid oscillation in distribution function attributed to the dephasing in the correlation between the quasi-particles pairs. After that transient state, that quasi-particle becomes separate out, and this stage is called residual electron positron plasma state. At this, we get the real particles. After that, and
okay, 2 minutes, please.
Okay. We also see the dependence on the longitudinal momentum, where we see that on changing the longitudinal momentum value, that pattern of that 3 stages are changes, and that mainly the transient state structure are changes, and that on increasing the longitudinal momentum, that oscillation becomes narrowing, and due to the vacuum polarization effect, we also look for the longitudinal momentum spectrum for taking that consideration at finite time. We see from early times to the finite. In early times, we see that it peak at 2, and as time proceed, its peak is shifted. The peak is mainly shifted due to the acceleration due to the electric field, and that is depend on the canonical momentum by the vector potential at we see at E tau P minus 2 to plus 2 to minus 2, and after that crossing tau means the pulse width of the electric field. We see some disturbance near the longitudinal small window, and in that window, as we progress in time after t equal to 2 tau, we see that secondary peak are dominating gradually, and we see after that at 3 tau, we see that become dominant and oscillatory behavior is shown, and this oscillatory behavior is due to the quantum interference effect, and this quantum interference effect comes due to the dynamical tunneling, and that dynamical tunneling can be considered or understood as a process that developing time in momentum space, where in which there is different channel is possible to particle can tunnel through. At a particle with there are 3 different stages, maybe we can example it that a particle with momentum p at early times, particle with p minus delta p, and particle with p plus delta p at
Okay.
and earlier times. And after that,
we need to get to the conclusions. Okay.
Okay. As we proceed in time, that oscillations becomes vanished due to that factor that exists in the hypergeometric function that comes in distribution function. After that, after we also see the effect of transverse momentum on longitudinal. So main effect is that on increasing the transverse momentum, the oscillation in the finite time is nearly washed out, and due to the as transverse momentum increases, the transverse energy also increases, due to which the less number of particles created, and we may cause the loss of coherence, and due to which the oscillation becomes invisible. And summary of the talk is that we find out the exact solution of the Dirac equation using that we says that there is a quasi-particle state following the transient state, out state where the real particle is formed at finite times, and that finite times provide a more physical information on non-equilibrium state. We also seen that longitudinal spectrum that exhibit oscillation at finite time. This oscillation structure can be understood as the tunneling picture, and this oscillation can also be understood as the electron escalation and de-escalation during the formation of electron positron using the vacuum polarization function and its counter term Vp, which are detailed in the recent we preparing a paper that we see in that. And we demonstrate that some generic spread of transverse momentum play a significant role in pair production at finite times. That complex behavior becomes shape pair for higher transverse momentum. This formation at finite time of particle number can enhance our understanding of designing the laser pulse. Thank you for attention.
Okay. Thank you very much. I mean, lots of information here. A very nice work, but very short time, unfortunately, to present everything. I'm not sure if there is any comment, very quick comment on the work. We are already past the time. Well, if not, let me thank Deepak Shah for his presentation. You were running to get on time. We just had a very short time, but thank you very much for your presentation. It was very nice, very nice. And I also would like to thank all the speakers for their very nice presentations. This was a very nice session. Thank you all for coming. And don't forget that tomorrow at 10 a.m. UTC, we'll return for the next sessions of Seminar 9. So thank you all for coming and for your presentations.
And thank Luis
thank
for
you.
this very tight schedule.
Yes, it was.
Take care, guys.
Thanks a lot to both the chairmans today, to Katarina and to Luis. Well done. Not easy with so many talks. So have a good evening, everybody.
Okay,
Bye.
thank
you.
Have
for the
a good
great
evening.
Talks. Okay, bye.
Thank you for the good talks. Okay, thank you.
Yeah, bye.
Recording stopped.